Okay, let's take a look at today's stuff. So finally, we'll get into some content, and we're gonna today's topic is just the basics of modeling. Okay, and so modeling here, of course, we're talking statistical modeling, and this is what we'll look at. Okay, so let's talk models and machine learning. And so first of all, what is machine learning even in the first place? And so this is what Wikipedia has to say. Wikipedia says machine learning is the scientific study of algorithms and statistical methods that computer systems use to effectively perform a specific task without explicit instructions, relying on patterns and inference instead. So it's kind of the idea that, we tell the computer, please learn some patterns, and based on the patterns you encounter, figure out what you're supposed to do, rather than saying, fit exactly this way or that way, right? And so the idea is, I say that the big idea is that what we're trying to do is we're trying to fit a model to data, okay? And people, of course, we still have to make decisions regarding the specifications of the model, what this model is going to look like. But a lot of the decisions, other decisions, are guided by the data and the algorithms that we use, okay? And so the decisions made by the algorithm, those decisions we can say is the machine learning part, okay? But of course, like, which model are we going to use? What this model is going to look like, that's up to the human. So it's not, I mean, maybe at some point the computers will get smart enough to figure these things out on their own, but right now they're not. And so, you still have good jobs, and they're not going to be taken over by the computers just yet. You still have to specify exactly how these models are going to get set up, and then you let the computer do that work for you. All right. So, when we talk about statistical models, okay, we can just think about a model. And so this is a model airplane. All right. It's a model airplane. It's not the actual airplane. It's a simplified representation of something complicated. Right. So, so what we have here, when we talk about a statistical model, it's a simplified representation of something, probably that's actually really complicated in the real world. Okay. So in the real world, there's some process that generates data, and the statistical model is going to be a simplified representation of that, right? So when we talk about data in the real world, it could be, how do we explain, all of, like, your cell phone is being tracked, and everybody knows your location and stuff. And so how do we explain the flow of traffic and all of this kind of stuff? Well, it's actually quite complicated if we think about the real world process, because this person lives over here and they chose this location because, I don't know, their parents are close by and their job is over here. And so there's all sorts of things as to why, like, somebody's located here and their job is over here, and they chose to drive this way, and maybe they make a stop at McDonald's on the way. It's like just too much stuff as far as the real world process goes. But we can create a statistical model that just says, oh, you know what? Downtown is where the jobs are, the suburbs is where the houses are, and we're going to just see kind of a flow of people going from the suburbs to downtown in the morning, and then in the evening we're going to see flow in the opposite direction, right? That's a simplified representation of, the complicated thing is, like, how someone chooses where to live, who ends up with what job, where those jobs are located. So that's all that we're trying to do, right? And so, this is basically what I'm trying to say here, is that the process that generates data in the real world is complicated. There are tons of little things that ultimately determine the outcome. And when we talk about a statistical model, as this is just going to be a simplified representation of that, okay? We're just going to look at the relationships between variables that exist, and we're only going to look at a subset of variables that are related to the outcome. And everything that we can't model, all the little specifics and all the little details that maybe if we knew more things we could explain, we're going to just encompass those in what we call an error term, or the residual, okay? The residual, or the error, is just going to capture everything else, and hopefully the part that we do model, hold something useful that we can do something with. Okay. There's a famous quote: "All models are wrong, but some are useful," by George Box. Okay. And that's the truth, is that, all of these models that we're going to create, none of them are going to explain everything. Okay. There's always going to be some kind of error, some kind of residual, something left over. Okay. And that's the part where we say all models are wrong. But indeed, a lot of the models are useful. Okay. And so I would say there's two kind of primary uses that we have for statistical models. One is that we can use models to make predictions. So we want to predict whether this outcome is going to happen or a different outcome is going to happen, or we want to predict some number. Okay. And we can use models to make predictions. Okay. And another use of models is to gain understandings of the relationships that exist between variables, right? So maybe we want to say, when this variable increases, it has an influence on this other variable. When this variable decreases, or maybe it has an influence over it, when we see this number decrease, we often tend to see this number also decrease. Maybe they're connected, maybe they're not. Maybe one is causing the other, maybe neither is causing each other, but we do see these things going together. We see some kind of relationship, some kind of association between these variables, and we want to kind of try to understand what's happening there. And so the models can be used to kind of gain that understanding. And sometimes we have to make a choice, right? It would be nice if we can make good predictions and we can understand the relationship. But the fact of the matter is, some models are better for understanding relationships, and they make okay predictions, right? And other models are really good at making predictions, but it's almost impossible to gain any kind of understanding out of them. Okay, and so that's those are some of the choices. We might have to make some kind of choice like that. Okay. All right. So here's an example from the textbook. Okay. And again, the textbook we're using is a first course in machine learning. And again, I apologize that this is a textbook that is not freely available, that you actually have to spend some money on. I generally try to pick books that you don't have to pay for, but I couldn't find one that I really liked for this class. So the example is on the Olympic men's 100-meter race. This is the foot race that Usain Bolt runs and stuff like that. And we're looking at the gold medal time for the 100 meters track and field event, right? And we're looking at so that's the outcome. And in the real world, there are just tons of different factors that go into the winning time, right? Why was one year faster than another year? And it all depends on the individual and, I don't know, track conditions and things like that. And what we're going to do is we're just going to try to make a simple model. Okay, we have a question. It says, is the book from the UCLA store the hardcover, softcover edition? I think the UCLA store says they're going to stock the paperback softcover edition because it's cheaper. And so, so they're going to do that. I know there is a PDF version, an unauthorized PDF version floating around on the internet. I can't encourage you guys to do that. I would get in trouble with the publisher. And so please don't put that link on the campus wire or anything like that. But I do know stuff like that exists. So, okay, let's see here. Okay, so this is the data, and it shows the year and the winning race time, and here's a plot of it. And what we see just overall is that there's just this general downward trend that shows that as the years went by, the speeds have gotten faster. Okay. And I think in the beginning, in 1896 and 1900, their stopwatches only recorded to the nearest full second. So it was either 12 seconds or 11 seconds. And I don't know what, what technology they had for recording race times, but it wasn't very complicated. Now you have like these super cameras that really get down to the, thousandth of a millisecond and stuff like that. But what we see is we see this trend, this downward trend that as time goes on, people get faster. Obviously, this trend isn't going to continue forever. We're now, if we continued extrapolated forever, we would end up with negative race times, and we know that's just not possible either. But overall, we would say, race times have gotten faster, okay? And what we have is so we're going to start off with a linear model. And what a linear model says is that the amount we would adjust our prediction, that remains constant through time, okay? So what we're going to do is we're going to fit a straight line model. And the key idea of the linear model is that the change remains the same, right? From 1920 to 1924, let's say our prediction changes by 0.05 seconds, okay? From the year 2000 to the year 2004, we're going to change that by 0.05 seconds as well, okay? If you have a nonlinear model, it means over here, you're going to change by 0.05 seconds, and then over here, you're going to change by something else, 0.08 or 0.02 or something like that, right? If a nonlinear model means, it's different over here and it's different over here. Okay. So, obviously we can't predict values in the distant future, but it could still be a useful model, okay? All right, so what we're gonna do is we're gonna fit a straight line to the data, okay? And when we do that, we need to fit a slope and an intercept, okay? And so fitting a model in this case is a process of trying to estimate the model parameters. We're trying to estimate what is the best slope, what is the best intercept that we want to use, right? And you've already learned this, right? You learned how to fit the slope and intercept from your 101A class and stuff like that, okay? But we're going to take it from kind of a machine learning perspective, right? And we want to find the slope and intercept that does the best job of fitting the data. All right, so what exactly does it mean to do the best job of fitting the data, right? So when we talk about the best parameter estimates, how do we define what the word best is, okay? And so how we define what best is very important, and that's going to be carried out through our choice of the objective function. Okay, let me go ahead and give you your first quiz answer. Your first quiz answer for today is the letter C. The letter C as in cat for Wednesday. First quiz answer is C, C as in cat. All right, so for ordinary least squares regression, okay, when we talk about OLS regression, best is the model that minimizes the total squares of the residuals, right? So residual is how much the difference between the actual value and what we predicted. So, if the actual value is here and we predicted this value, this distance is the residual. And least squares regression says, we're going to square all of these residuals, and we want to shrink. We want the slope and intercept so that the squared residuals are as small as possible. Okay, and so we're going to say, the RSS, the residual sum of squares, is the difference between the actual value y and y hat we squared summed up. Okay, and we want this to be as small as possible, right? So I'm assuming this is okay with everybody. And so, a consequence of using the squared residual function is that squared error penalizes large mistakes more heavily than small mistakes, right? So, because when you square 1, you get 1, but when you square 10, you get 100, right? And so if your residual is 10, that's a much bigger mistake, and that's going to influence it a lot more and things like that. So that's why our ordinary least squares is greatly affected by outliers and stuff. Okay, so anyway, this thing is the thing that we want to minimize, and we're going to call this is our objective function. This is the objective. This function tells us what we're trying to accomplish, okay? And we're trying to make this as small as possible. So this objective function is also called a loss function or a cost function, okay? Because, you know, in general, you're trying to minimize your losses, you're trying to minimize your costs, okay? So we're gonna say we wanna shrink this as small as possible, we wanna minimize our loss, we wanna minimize our cost. So this is also called the loss function or cost function, okay? And so a lot of machine learning models, and that includes linear regression, okay, are done by trying to fit parameters that try to minimize or maximize some kind of objective function, okay? And so a lot of these machine learning problems can be reframed or thought of as optimization problems. We're trying to optimize some kind of function, right? Optimization is all about finding the local min or you know, a min or max of a function. And so when we're talking about minimizing the residual sum of squares, that's effectively an optimization problem. Okay, and so even though this linear regression, you know, is going to be reviewed for you, we're going to start here because I can introduce a lot of these machine learning concepts. Okay, I'm going to try to match the notation in the textbook, and so they don't use y and y hat. Okay, they use the actual values is t. Okay, t as in target value. This is the target value. And the value predicted by the model, instead of y hat, they're going to just show it as explicitly the result of the function when you plug in, you know, your x. Okay, so instead of y hat, we're going to have f of x of n, where the parameters are w0 and w1. Okay, so this is just to say the y hat, the value we're predicting, is a function of xn, where the parameters of this function are w0 and w1, okay? And rather than using the total squared error, it uses the mean squared error. So we're going to do 1 over n times the sum of squared residuals. And if I use the notation in the textbook, the loss function, which has this curly L, is going to be 1 over n times t sub times the sum of t sub n minus f of x of n with parameters w0 and w1, that quantity squared, right? But this is still just the residual sum of squares, but now 1 over n, so just the mean squared error here. Is that okay? Mean squared error, MSE, is this going to be this function? Okay, another function that, this is a bit of a side note, that we try to optimize is the root mean squared error, RMSE, and so you might often see people talking about RMSE. That's the root mean squared error, and that's basically the mean squared error minus you take the square root of that. Okay, and basically, if you find parameters that optimize the residual sum of squares, the same parameters that optimize the residual sum of squares are going to be the same parameters that optimize the mean squared error, and it'll be the same parameters that optimize the RMSE. So we don't have to make a huge deal out of it, okay? And that's because the square root function is monotonic. So basically any value that minimizes this will be the same value that minimizes this, right? Because if a is greater than b, then square root of a is greater than the square root of b for all values of a and b. Okay, so as far as linear regression goes, we've got the two parameters, the intercept and the slope, and we want to find the intercept and slope that are going to minimize this loss function. Okay, so if we talk about what value does this function output, right, for w0 and w1, okay, if we plug in some value xn, the output of this function is going to be the intercept plus the slope times x. Okay, and so I'm going to just plug this in to the loss function. Okay, and so this is the loss function, and it's going to be t sub n minus the quantity w0 plus w1 xn. We're going to take that quantity, we're going to square it, add them up, 1 over n. So this is the loss function. I'm just replacing the f of x with the actual quantity w0 plus w1 xn. Okay. So far, so good? Okay, thanks. Thanks for your head nods. It's encouraging. Okay, all right. And so what we can do, I'm going to just start off by say, let's try to minimize the loss function using calculus, okay? And so to minimize the loss function using calculus, we're going to treat the observed data, which are our x values and the target values t, we're going to treat those as fixed, okay? And the value of our loss function, that is the sum of squared residuals, or the mean squared error here, is going to be, depends on our W0, our intercept, and our slope terms, W1. And we want to find the values of W0 and W1 that are going to minimize our loss function, okay? And so we're going to say we want to find the W0 hat and the W1 hat. Those are going to be the values that minimize this function, okay? And that's going to be this, okay? And so so I'm going to plug this in, okay? And so this is what we're looking for. We're looking for the W0 and W1 that minimize this thing. And I'm going to go ahead and I'm going to just expand this, right? So this is just a whole bunch of algebra mess, all right? And so we're going to get if you do this, you get W1 squared xn squared plus 2W1 xn W0 minus Tn plus W0. Okay, so anyway, just trust me. You're going to just have to trust me on the work here. I mean, you can do it yourself, but you'll just have to trust me on this, okay? And then to do this with calculus, we're going to find the partial derivative of L with respect to W0, set that equal to 0. We're going to find the partial derivative of L with respect to W1. We're going to set that equal to 0. And then we're going to solve for W0 and W1. Okay. Did you guys already do this in like 100B? Okay, you guys know, maybe? 100C? Maybe, maybe not. Okay. So maybe you've already done this. I see people nodding their head and some people shaking their head. Sort of. Okay. Well, I guess that's good enough. All right. Well, maybe just the idea makes sense, right? You're going to take the partial derivatives. You're going to set them equal to 0. You're going to find out where the derivatives are 0. Okay. And right. So I don't know. When did you do partial derivatives? That's 31B. I don't know. 32B, something like that. 32A, something around there. Okay. We're just making up numbers here. You set those equal to 0. Okay, so I skipped a bunch of steps. The details of getting the partial derivatives is shown in the textbook, section 1.1.4. Okay. All right. So anyway, if you take the partial derivative with respect to W1, this is what you're going to get. You take the partial derivative with respect to W0, this is what you're going to get. Okay. Came a lot with moment generating functions. Oh yes, moment generating functions. So anyway, if we take the partial derivatives, this is what we do. We're going to set this equal to 0, and then we're going to solve. Okay. So I skipped the steps for the partial derivatives, and so anyway, if you do this, you're going to get some formula that we can use for figuring out the slope and the intercept, right? Okay. What I'm going to do here is I'm going to transition things into linear algebra. So I don't know, when you did this, did you solve it using linear algebra? Or did you do with part, I don't know. Okay. Yes or no? I got people saying different things. Okay. So because we're dealing with multiple observations, having this summation term here, all right, these summation terms in the loss function and here, they can be annoying to deal with, right? When you're dealing with summation terms, you know, sometimes you can just kind of like move the summation term around, and the other times you're like, oh, it's attached to the x, and so then I can't mess around with it. A lot of times if we can turn things into matrices and use linear algebra, then we don't have to worry about the summation, because matrix multiplication already includes summation, right? If you take a column vector and a row vector and you multiply those, you're basically doing multiplication and summation, right? So because the column times a row, you're going to just get one scalar value, and so the matrix multiplication includes the summation in there, right? And maybe it's been a while since you took linear algebra, or maybe you just finished 115A. So I don't know what, but this is a very, very, very good playlist that I strongly encourage you to watch, by 3 Blue 1 Brown, one of the best YouTubers out there. Everybody should subscribe to his channel, and this is on the essentials of linear algebra. Some beautiful animations that were made using Python, and so watch all of these things, and anyway, well, at least watch the things on, like, well, I guess vectors is a good start, and then also things on like the linear transformations and matrix multiplication as composition. So these are very good, but all of the videos are excellent. Okay. And so I'm going to kind of show you the same kind of stuff where we're going to use ordinary least squares regression, but using matrix notation rather than getting into the partial derivatives. Okay, because I think either you've seen the partial derivative stuff already, maybe, but you can also figure it out too. All right, let me give you your second view quiz answer for today. Second view quiz answer is D as in dog. D as in dog for your view quiz answer. Okay, so our intercept and slope we're going to store in this column matrix. Okay, this 2x1 column matrix W. This is going to be our matrix of parameters. Okay, and then one single observation is also going to be this 2x1. So that's going to be little x sub n is 1 and x sub n. Okay, and the reason why I have this 1 here is that because I want to express our prediction, which is W0 plus W1 xn. I want to express that as a matrix multiplication operation. Okay, and so if I do W transpose, so that's going to turn that into a row, and times xn, this column. When I do that, and I have the row multiplied by the column, I'm going to get a scalar value, and the W0 multiplies by the 1, and the W1 multiplies by the xn. Okay, and so our x matrix x sub n is going to be this 2x1 column matrix as well, right? So is that okay? Expressing just the prediction for observation xn is W transpose times xn. Okay, so we're going to express our predictions using this. Okay, so that's great. So what we're going to do then is we can expand this, and so now I have big X. Okay, so back here I had little x sub n in bold print to indicate that it's a matrix or vector. Now I have big X. Okay, and if you're doing this handwritten, you just put little arrows over the things, right? Or little arrows for vectors, and then you kind of I add serifs to my X to indicate that it's a matrix. How do I show you this? I don't have my so this would be the see this. Okay, so I do the little arrow to indicate that it's a vector. So that's x, little x sub n, and then I add the bars over the x to indicate that it's like big matrix X there, the serifs, the feet on there. Okay, but anyway, but on LaTeX it looks nice and pretty here. So so big X is going to be all of the xn vectors for all of our things, but we transpose them. So big X is going to be a n by 2 matrix. Okay, we have n observations, and so basically we have a column of ones and the column of x values. Okay, this is a n by 2 matrix, and then T is our target values, and this is just a column of target values, so that's going to be n by 1. And the loss function, which is basically the target value minus the predicted value squared summed up, can be expressed as this, and I'll show that on the next slide here. Okay, so the loss function is the mean squared error, and so yeah, so that's the next few slides. Okay, so I will demonstrate that we can express the loss function just as this. Okay, so the column of values predicted by the function can be expressed as xw. So big X, okay, big X is again our n by 2 matrix, and we're going to multiply that by w, which is a 2 by 1 matrix. So when I do n by 2 by 2 by 1, I'm going to get an n by 1 matrix, right? And this is going to be all of the predicted values. It's going to be w0 plus w1 times x1 for the next observation, w0 plus w1 times x2, and so on and so forth, w0 plus w1 times xn, okay? And when you're working, especially on hand, when you're working on writing things down by hand, you're going to be doing a lot of matrix multiplication in this class. And so I want to make sure you guys get into good habits here. It can be confusing whether you should write capital X times W or little w times capital X or things like that, right? Which order is going to work, right? And so I strongly encourage you, always put the dimensions underneath the matrix or vector, okay? And because the rule is when you do matrix multiplication, the inner dimensions have to line up, okay? If you're gonna have an n by 2, the next thing has to be 2 by something, okay? And so you can do n by 2 times 2 by 1, but if you flip these around, you can't do a 2 by 1 times an n by 2. That's not gonna work, okay? So always write the dimensions, and this will help you avoid a lot of heartache and mistakes, okay? So n by 2 times 2 by 1, and that's going to result in an n by 1, right? So these inner dimensions must always match, right? So because if I do this, right? So here, let me just do these matrix operations in R here, okay? So X is the vector of year values, so like 1900, 1904, 1908, and stuff like that. N is the length, and I'm going to create a column of ones, and I'm going to create X by binding the ones with the X, right? So X is a 28 by 2 matrix, an n by 2 matrix, and then W is a 2 by 1, and so here I just have the value 1 repeated, okay? 2 rows, 1 column. The dimensions of W is 2 by 1. And here, if I try to say, okay, if I do X times W, this is matrix multiplication in R is the percent star percent sign. So if I say, what are the dimensions? What's the dimension of X times W? That comes back and it says 28 by 1. Here, if I try to do W times X, I get an error. I get non-conformable arguments, right? And this is a very common mistake. And so if you see this argument pop up, non-conformable arguments, that means the dimensions don't apply, right? Don't align properly, because here W is a 2 by 1, X is an n by 28. It's not going to work, okay? And so, or I'm sorry, X is n by 2, 28 by 2. So I've got a 2 by 1 times a 28 by 2. That's not going to work. I have to do it the other way. So you can often kind of figure out the problem if you write out the matrices, write the dimensions underneath them, make sure they align properly, and that's going to help out a lot. Okay, so if we talk about the residuals, the residual values, the column of residual values in a matrix is going to be T minus XW, right? So XW is a column of n by 1 values, and is an n by 1 column of our predictions. W, our predictions is XW here. And T is also the n by 1 column vector of target values. And so this represents my residuals. T minus XW, and this whole thing is an n by 1 column, right? So this is, it looks like a mess, but this is just one column, an n by 1 column of values, T minus XW here. Okay, and so if we talk about the sum of squared errors, right? So the sum of squared errors is Tn minus W0 plus W1 xn, squared summed up, okay? I can expand this out, which will be T1 minus W0 plus W1 x1. And then the next value is T2, W0 plus W1 x2, all the way to Tn, W0 minus W0, W1 x1, xn, okay? And if I take that, so that's the row, multiplied by the column, you can see that this thing, this times this is equivalent to this, right? Because I'm taking each of these things, this is going to get multiplied by this one's going to get multiplied by this, so on and so forth. This last one is going to get multiplied by this. So we're effectively squaring all of the values and we're summing them up when we do this matrix multiplication. When I take this row vector and multiply it by this column vector, I'm taking each of those things, I'm multiplying this item with this item, the next item with the next item, the next item with the next item, so on and so forth, down across the row and down the column, and we're adding them all up. And so this whole entire summation, the sum of squared errors, can be expressed as T minus XW transpose to turn it into a 1 by n row vector multiplied by T minus XW, this column n by 1 vector, right? So I've got so here I have a 1 by n, T minus XW transpose is 1 by n, multiplied by T minus XW, which is n by 1, okay? And so these two are gonna, their dimensions align, and we get a 1 by 1 scalar, and I'm going to multiply that by 1 over n, okay, or divide by n to get the mean squared error, and that's my loss function. Is that good with everybody? Setting this up as a matrix multiplication for the loss function. Okay, so here I'm going to, so we have T minus XW transpose times T minus XW, and I need to, I want to expand this out, okay? So I don't know if you remember your rules of applying transpose into things, but here for addition and subtraction, the transpose applies to the individual elements being combined, and you don't have to switch any elements here. So you got T transpose minus XW quantity that item transpose, okay? But then when you distribute a transpose across things that are being multiplied, you have to swap their orders, right? So XW transpose becomes W transpose X transpose. Is that okay so far? So I got T transpose minus W transpose X transpose times T minus XW. And now I have to multiply these two things together. And so here I'm going to just, first, outer, inner, last elements, things like that. So I got T transpose T, right? T transpose T is going to be 1 by n times n by 1. So that's going to reduce to a 1 by 1. Then we do the outer elements, T transpose times XW, which is going to be T transpose is 1 by n, X is n by 2, W is 2 by 1. Okay, so that works out. That's going to be 1 by 1. Okay, then the inner elements, W transpose X transpose T, okay, 1 by 2, 2 by n times n by 1. That's going to also combine to a 1 by 1. And then W transpose X transpose XW, okay? And this also combines, no problem, okay? So, so these are all 1 by 1s, and they will all add together, okay? And I think I explained this on the next slide, okay? Is that I can combine T transpose XW with W transpose X transpose T, because these are transposes of each other. And so this will become T transpose T minus 2 W transpose X transpose T plus W transpose X transpose XW. Okay, and then if I throw in a 1 over n term, this is a 1 by 1 scalar, right? I'm adding a whole bunch of 1 by 1 scalars together. I can throw it over 1 over n, or multiply 1 over n times it, and we're going to get our loss function here. So here I'm just expanding out T minus XW transpose times T minus XW into this. Okay, and then these terms, T transpose XW and W transpose X transpose T, these are transposes of each other, right? So if I take the transpose of this, we would flip the order of the multiplication and add transpose terms to these things. And a transpose of a transpose is the original value. And because they are also scalar values, so these are transposes of each other and they're scalar values. So they're one by one thing. So a one by one transpose is still a one by one. So they're the exact same value. We can combine them. So that's why I was able to combine these two things into that. Okay, and so what we want to do now is we're going to take our loss function and we're gonna minimize it, and we're gonna minimize it using calculus. Okay, we're gonna do vector calculus, and so so we're gonna take the derivative. We're gonna set the derivative equal to 0, and then we're gonna solve for w. But this time w is a vector. All right. So I'm not sure if you guys have done like vector derivatives and things like that. But we can do it. Okay, so we're going to do a little bit of just a touch of vector calculus here, and we're going to take the derivative with respect to w, which represents our slope and our intercept, and we're going to set it equal to 0. Okay, so just so you know, when you do derivatives, this is what a derivative looks like, right? This is the definition of a derivative. You got some function that goes from one value in the real number line to another value in the real number line. And we say the derivative of f prime is the limit as h goes to 0 of the difference between, you know, the function plus a tiny little value, the function of x plus h minus the function at x. Okay, and then we just take that difference. And this is the definition of the derivative. And an alternate way of expressing the derivative is that we're going to say that the derivative f prime satisfies this thing, or that as h goes to 0, this whole thing is also going to go to 0 as well. Okay, and so the analog to a derivative when we're talking about a vector or something in a higher dimensional space is called the gradient. Okay, the gradient. And so what a gradient does is, you know, we want to find the gradient of a function, and this function is different from a regular, just a univariate function, in that the input to the function is multi-dimensional, right? We're not going from, you know, your input is not just one value x, it's a vector x of n. In our case, it's a vector w, or we've got a w0 and a w1 term. Okay, and so we're basically existing in some n-dimensional real space, but the function outputs a single value. Okay, it outputs a scalar. It outputs our loss function when we're talking about the sum of squares residuals. The input is vector, two values, the intercept and the slope. The output is the sum of squared residuals, which is one value. So that's what we have. We're going from n-dimensional space, and the function outputs one value here. Okay, and the gradient, which is written with this upside down triangle, the upside down triangle is called the nabla, right? So I always wanted to call this delta, but delta is a right side up triangle, and when it's an upside down triangle, it's called nabla. Okay, so this is nabla f, and that's the gradient. Okay, and it's basically it's like the multi-dimensional derivative. Okay, it's kind of like the multi-dimensional derivative, and it tells us how the function changes with respect to each component in the vector. Okay, and it's going to satisfy kind of this parallel equivalent to this thing. Okay, and this is a zero vector here. All right, and so what it will become is, if the input of the function is some vector w, in our case, we got a vector w of intercept and slope terms, but you could have just some n-dimensional vector w, right? So you can have, it could be in 17 dimensions, 80 dimensions, however many dimensions, okay? The gradient of the function, okay, with respect to w, okay, is going to be a vector itself, okay? And it's going to be, the vector is going to be, it's basically going to be a vector of partial derivatives. Okay, it's going to be the partial derivative of the function with respect to W1, partial derivative of the function with respect to W2, all the way down to the partial derivative of f with respect to Wn. Okay, and so the important thing is that this vector W and its gradient will have the same dimensions. Okay, W is technically a column vector, but I'm representing it as a row for simple illustration here. Okay, so so if W is some vector of length n, the gradient will also be a vector of length n. Okay, they're going to have the same dimensions. Okay, so like the derivative, the gradient represents kind of the slope of the tangent of the graph of the function, but a little bit more specifically, the gradient is going to point in the direction of greatest increase. Okay, we call it the greatest ascent, steepest ascent. The gradient points in that direction. Okay, and the magnitude of the gradient, that vector, is going to be the slope of the graph in that direction there. Okay, so we're going to run out of time here, but some important gradient relations here is, let's say you have some function, okay, and it's a 1 by 1. Remember, our function outputs a scalar value, okay? So when you take the gradient of the function with respect to W being a 2 by 1 matrix, you're going to get these results, okay? So if you have W transpose X, which is a 1 by 1 scalar, 1 by 2 by 2 by 1, when you take the gradient with respect to W, you're going to get X, which is going to be 2 by 1. Okay. If you have X transpose W and you take the gradient with respect to W, you're going to get 2 by 1. Sometimes students ask, why am I not getting X transpose or X transpose over here? Okay. And the answer is again, the resulting gradient needs to have the same dimensions as W. Okay. And W is a 2 by 1. So the result needs to be 2 by 1. Now there's a typo here. It says X and W, it should be, it says W and W, it should say X and W. So if you have W transpose W, okay, then the gradient is going to be 2W, okay? This is almost like W squared. So in the same way that, like, what's the derivative of X squared? The derivative of X squared is 2X. It's kind of like that. The gradient of W transpose W is going to be 2W, okay? And here, if you have some square matrix C, okay, you get W transpose CW. This is going to be 2 CW is the gradient of this, right? So if you have some value, that's going to be the gradient. Okay, so what we're going to do is we're going to apply this, and what we'll do is I'll continue this on Friday. Is we're going to take the loss function, which is what we have here, and C needs to be symmetric. I'm trying to think here. It needs to be 2 by 2. I'm wondering if it needs to be symmetric or not. Let me get back to you on that. But what we're going to do is we're going to take the gradient of the loss function with respect to W. Okay, and this is we found the loss function equal to this, and then we're going to take the gradient with respect to W. We're going to set it equal to 0, and then we're going to solve. And that's what we'll do on Friday. Okay, so you can kind of preview these notes, but we'll work through them on Friday to talk about taking the gradient there. Okay. I'll also probably try to post your first homework assignment sometime between tonight and Friday, and then I'll make sure you have adequate time to get it done. There's going to be a lot of stuff that we haven't covered yet in your first homework assignment, so you can get started, but don't be surprised if you can't do everything just yet, right? So because I haven't covered everything. Okay, last quiz answer for today is the letter B. Letter B is the last quiz answer for today. Letter B. All right, we'll end here for today, and we will see you guys on Friday.